I'm Bruce Bugbee, president of APOGEE Instruments, and I want to talk in the next few minutes about photobiology and how ratios of colors of light affect both plant shape and plant growth. And by plant growth, we mean photosynthesis. So these are two different things. Now, many papers have been written on this. My laboratory at the university has published extensively on this. I've spoken many times on this. This is a bit like diet and people. What's the perfect diet for people? Well, different diets vary for different people. But I want to try and capture the elements of this very simply to show you the concepts of it. So we're going to take plant growth. Let's start with colors, and we're going to start right here with 400 nanometers. This is roughly the start of human vision, and we're going to go over here to 700 nanometers. And right in the 500, here's 500, here's 600, and over here we'll put 800. So these are the wavelengths associated with colors of light. Now, if we do blue, this is blue here. This is elementary, but it's important to the understanding. This out here is red. And green right here. GRN, green. These are the three primary wavelengths that drive photosynthesis, and they're roughly equal, which is why we get photosynthetic radiation, and we say that's equal across here. All these colors contribute equally. In truth, we know they're not quite equal. The blue is a little less. The curve is something like this for plant growth, but we still count them equally. But the issue here is not so much plant growth, but plant shape. Plant shape is what we can manipulate with colors of light. And now we have to add in the far red out here, and that's generally up to 750 nanometers. So here's far red. We also need to add in the UV down here, and this is another little edge right here from 350 up to 400. This goes shorter than this, but this is the beneficial UV. Shorter than this is usually bad, but there's a lot of good effects of UV from 350 to 400. All right, 1, 2, 3, 4, 5 categories of light. The most efficient LEDs are reds and blues. So for a long time we had only reds and blues and magenta LEDs. We still have those because these two colors are efficient. But now we know the green photons are just fine. They cause excellent photosynthesis. They penetrate deep into canopies. There's a lot of good reasons to have some green in your lights. Plus, these are the photons that humans can see really well. So we want some green in. So the most efficient LEDs are the whites have, let's see if I can put this in blue, have a lot of blue light, and then they fluoresce in the green and taper off. See if I can make that go up. This is generally a white LED, and it's a cool white. Cool white means it looks very white. There's a lot of blue light in there. This is the most efficient color of white LEDs, is blue LEDs. That most of the research has gone into these. These have come a long ways. But here's the problem. The blue light causes a little less photosynthesis, but more importantly, blue light shrinks plants. So you get all that blue light and you get a small, compact plant. That's often considered bad, but it depends. If you plant at a higher plant density, compact plants can be very good. In indoor agriculture, we want short plants. So high blue light is not necessarily bad. And that's also a very efficient LED. But here's the key. If we take a cool white LED with high blue and compact, now we can add out here some far red. And far red does the exact opposite of blue. This expands plants. It makes the leaves expand more and it makes the plants get taller. So the cutting edge of research now is the combinations of far red and high blue light to shape the plants. And we turn the dials. We want tall plants, we want short plants, wide plants. These are the two primary colors that we use to shape plants in different ratios. These are efficient LEDs, and so are far red efficient LEDs, and so are the whites. So we can rearrange these colors. By this analysis, the greens and the reds become like filler colors. They cause photosynthesis, but they don't have the power to shape the plants that the blue and far red photons have. So this is a concise summary of work in my laboratory that we're doing to shape plants. Lettuce is in a unique category. Lettuce responds very well to far red. It expands the leaves, it causes rapid growth. This is terrific. But if you give these far red photons to tomatoes, they mostly get taller, and that's bad. Most crops respond to far red by getting tall. It's unfortunate. But lettuce and spinach and leafy greens respond to far red by growing more leaves. That's a good thing. So we can use far red to counteract blue for crops like lettuce. How about cannabis? Everybody wants to know colors of light. Cannabis, far red makes it taller, blue makes it shorter. So cannabis is more like tomatoes in this thing. We got to be careful not to give too much far red for cannabis because they get too tall. So this is a very concise summary of some of the cutting edge research and thresholds for light. Because far red is so powerful, APOGEE has developed a sensor that measures separately this PPFD in here. It has two detectors, and it has a far red detector out here. So it's two detectors in the same sensor, so you can tune your growth chamber to optimize it for both colors of light. Thanks for listening.